Thank you for joining. My name's Hevin, and I'm the author of Machine Learning with R, the Tidyverse, and MLR with Manning Publications. I am a life science researcher working at the Francis Crick Institute in London. And today I'm going to show you how to train, tune, and cross-validate a support vector machine model in R using the MLR package. So support vector machines are models for supervised machine learning tasks that could be, for example, for performing classification tasks, where we're trying to predict a set of discrete categories from our training data. Or support vector machines can also actually be used for regression tasks, where we are trying to predict a continuous variable. And both of these are examples of supervised machine learning, because when we present the training data to the algorithm, we give it data that has already been labeled. And so in the case of classification, you give it a set of data, and every case in the data already has a label indicating its membership to one or more classes. And so today I'm going to show you specifically how to train a support vector machine for classification. This is a sort of silly example that I've taken from my book, illustrating what support vector machine models aim to achieve. So support vector machines learn a hyperplane that extends through the feature space that best separates the different classes that you have in your data sets. Okay, in this silly example, I've got just two variables. So the money that you made your company this month, for example, and the time that you spent playing games at your desk this month, and you're trying to use this data to predict whether your boss is in a good mood or a bad mood with you, which is a very important machine learning task. And in this kind of very simple and contrived example, you can see that actually the classes are very easily separable, and there would be actually many different hyperplanes that could separate these classes perfectly. But the support vector machine algorithm for classification aims to learn the hyperplane that maximizes the margin around itself, that gap that separates the classes. And the reason that this is important is that based on the training data that you have, this will be the hyperplane that will generalize best to new unseen data that maximizes the margin around itself. And support vector machines are very powerful and popular. And one of the reasons that they're so powerful is that they can learn complex nonlinear decision boundaries between different classes in a data set. And that sounds like a bit of a contradiction in terms, because I just told you that support vector machines work by learning a hyperplane, which by definition is linear. But support vector machines are one of a set of techniques called kernel methods. And so support vector machines can actually add an additional dimension to your data, to your feature space, called a kernel function, that helps you to separate your different classes. So here's an example where I've got two different variables and with data belonging to two different classes, and there is no linear decision boundary here that could help us separate those two different classes. Okay, but the support vector machine can use a kernel function to add a new dimension to your data set that kind of stretches or deforms your feature space in such a way that now there is a linear hyperplane that exists that is able to separate the classes. And if we were kind of to project where this hyperplane cuts across this kernel function and project that back onto the original feature space, you can see now that by learning a linear hyperplane, the algorithm is actually able to learn a complex curved decision boundary and is able to separate these two classes. Okay, so I'm going to show you in R how to train a support vector machine model. So if you're used to programming in RStudio, then you may know, or you may find it useful to know, that the keys Control, Shift, and R bring up this window that allows you to specify a section. So I'm going to start by loading the packages that I'm going to use for this session. And the first package is the MLR package for performing our machine learning. The second package is, or set of packages, is the tidyverse, which is a collection of packages for data manipulation and plotting that my book discusses in quite a bit of detail. Okay, so next we're going to load the data set that we are going to work with, and the data set that I'm going to work with is the spam data set, which is part of the Kernel package. And this is a data set where every row corresponds to an email and every column corresponds to a variable or a measurement about that email. So it could be, for example, the number of capital letters or the number of URLs. And there is an additional column in this data set that is an annotation as to whether each email was considered to be spam or not spam. And so what we're going to do is train a support vector machine model to try to classify emails as spam or junk mail versus desirable mail, for example. If I check out this data set with the dim function for dimensions, I can see that this data set has just over 4,600 rows and 58 columns or variables. And this isn't a massive data set, but just for the purposes of today, to speed the demonstration up a little bit, I am going to downsample this data set to just 1,000 rows. And then I'm also going to convert it into a tibble. So many people in R are used to working with data frames as a way of storing rectangular data. The tibble is the tidyverse reimagining of the data frame. And we could continue the rest of this demonstration using data frames. That would be fine. But tibbles have a nicer way of printing and presenting the data. So I'm going to use that instead. So I'm going to call my object spam tib for spam tibble. And I'm going to use the sample n function to sample randomly 1,000 rows from the data set without replacement. And then I'm going to use the pipe operator to take the result of the function on its left and pass it into the function on its right. So this function is loaded in with when I load the tidyverse. And I'm going to pipe it into the asTibble function just to turn this 1,000 row data frame into a tibble. And now if I just print out this tibble, you can see that it only shows you the number of columns that will fit inside your console, whereas when you print a data frame, it sort of prints everything and you have to scroll up. It lists the columns that couldn't fit on your console, so you can see all of the variables, and it only shows you the first 10 cases in the data set. And another thing that I particularly like is that it shows you the column type, so whether it's a double or a factor or a character, for example. So this is our data set. Another useful function is the glimpse function, and if I wrap my data set in glimpse, this kind of displays the data in a different way. It sort of rotates it on its side so that now the columns are along the left hand side, and it shows you the first several values for the first several cases for every column. And this is a nice way because you can very easily scroll through and see all of the columns that are available to you in the data set. And this is that important variable down here, type, which is a factor that tells us whether each email was considered to be spam or non-spam. And actually, what it might be nice to do is if I give that column to the table function, we can just get a printout of the number of emails within each of those classes. So I've got 619 non-spam emails and 381 spam emails. Okay. So we're going to train a support vector machine model to classify emails into those two groups. So the first thing that we have to do when we're training a machine learning model with the MLR package is to define a task and a learner. Our task is simply a definition of the data that we're working with. And if it's a supervised machine learning task, we have to supply the target variable. Which variable are we trying to predict? And of course, in a classification task, this is a categorical variable. If it was a regression task, it would be a continuous variable. The learner is the definition of what algorithm we're going to use to learn our model. This also includes any additional arguments that we want to supply to control how that algorithm learns. So define task and learner. Okay, so I'm going to create an object called spam task, and the function to make a classification task is make classif task. If I was going to train a regression model, then instead this would be make reg task for regression. If I was training a survival model, it would be make serve task. And if I was training a cluster model, it would be make cluster task, for example. But in this example, this is a classification task. So I use make classif task. And I simply supply the data set I'm going to use as the data argument. So this is spam tib. And because this is a supervised machine learning task, we have labels that we're trying to predict. I supply the variable that we're trying to predict as the target argument. So this is the type variable. And when I run this, MLR will give me a warning that the provided data is not a pure data frame, but from class Tibble df. So the function expects a data frame, so it's giving me this warning. But actually, this does work. You can give the function a Tibble, and everything will continue as normal. So you can safely ignore that message. Okay, so the next thing that we need to do is define our learner. So I'm going to define a learner called SVM for support vector machine, and I use the function make learner. And MLR comes with a large number of machine learning algorithms built in, and you can also define your own if you want to. And all of the algorithms come with a two-part naming system. So every algorithm has a prefix and a suffix. And the prefix determines what kind of task the algorithm is used for, so classification, regression, etc. And the second part, the suffix, is the name of the algorithm. And so if we're performing a classification task, we'll use classif and then dot, and then the name goes as the suffix after the dot or the period. If we were doing a regression, then you've probably worked out it would be reg dot, or it would be cluster dot, etc. So this is a classification task, so classif dot, and for the support vector machine algorithm, it's simply SVM. This prefix suffix is important because some algorithms, just like SVM, can be used for both classification and regression. So this tells MLR that we want to use the classification form of the algorithm. Now there's another optional argument that is useful, and I would suggest that you set, is the argument predict.type. So by default, this argument is set to response. And what this means is that once we have trained our model and we give new data to the model to make predictions on, the model will simply predict the class that it thinks each case belongs to. So in this case, we give it a bunch of new emails, and the model will say, this is spam or this is not spam. but it doesn't give us any indication as to how confident the model is as to what the classification should be. And so instead, what I set this to for models or for algorithms that support this is I set this to prob. And so instead, when we train a model like this, when we pass it new emails, instead of just saying spam or not spam, it'll give us a probability based on how likely it thinks that each email is spam or not spam. And this is useful. It helps us make better decisions. It helps us use sort of human in the loop machine learning, because if a model is 99% confident that an email is spam, and that same model is maybe 51% confident that another email is spam, those emails will just be classified as spam, and we don't know that one is more likely than the other. Whereas if we actually inspect the probabilities, then we can create rules such as if you are less than 60% or 55% sure that an email is spam, don't flag it up as spam, or let me manually classify those emails or something like that. So I set this to prob for probability. Okay, so the next thing that I'm going to do is define the way that we are going to tune the hyperparameters of the algorithm. So a hyperparameter is a setting or a variable that controls how an algorithm learns from data, but is something that can't be learned directly from the data itself. So it's something that either we need to set or we need to tune in some kind of experiment. And the support vector machine algorithm has a few hyperparameters that we need to optimize. So I'm going to show you how to do that. Define hyperparameter search space. Okay. So if you're coming to use an algorithm for the first time, you may not already be aware of what hyperparameters it has and which ones you need to set or tune. And so the function get param set from the MLR package will show you all of the available hyperparameters for that particular algorithm. So if I pass this classif.svm, so this prints out the table, and every row in this table is a different hyperparameter, and we get told its type, so whether it's a discrete hyperparameter or numeric or logical. We get told what its default value is, so if we don't touch it, if we don't provide a value or ask MLR to tune the hyperparameter, this is the value that the algorithm will use. We get told the hyperparameter's constraints, so whether it's constrained to be a value between 0 and infinity or negative infinity and infinity. And we get told whether we are able to tune it. So not all of these parameters are actually tunable. Most of them are. And for the SVM algorithm, the most important hyperparameters for you to tune or to set are cost, kernel, degree, and gamma. So let me spend some time explaining what those guys are. I already mentioned that the SVM algorithm uses a kernel function to deform or stretch the feature space into a new dimension that helps separate the cases. And how the feature space is deformed and what kind of shape the feature space is deformed into depends on what kernel function we choose. And there are a few different kernel functions that are available to us. And these are some of the most commonly used ones. So one option is the linear kernel, which is actually equivalent to no kernel at all. We can use a polynomial kernel, which is able to create decision boundaries of increasing levels of flexibility. So as you go from second to third to fourth polynomials, you can have very flexible decision boundaries. The radial basis kernel, which is the default, is very, very good at identifying distinct islands of cases that belong to particular classes that may be surrounded by cases in other classes. And actually this here is an example of what a radial basis kernel might look like. And then finally, the sigmoid kernel, which uses the sigmoid function to deform the feature space. And this is sometimes useful if you have situations like this, where you have one class that is sort of bounded by another class on either side. And so our choice of kernel vastly controls the shape of the decision boundary that our final model will learn, and our model will perform better or worse in different situations, depending on which of these kernels that we choose. And so this is a discrete hyperparameter that we need to select. The cost hyperparameter determines how bad it is to have cases inside the margin. So in a perfect situation where there exists a hyperplane that perfectly separates the classes, that hyperplane will have a margin around it that has no cases inside it. Okay, and the further apart two classes that are perfectly separable are, the larger that margin will be. But in reality, in complicated machine learning tasks or problems, it's unlikely that we're going to have easy problems where the classes are fully separable. And so it's very likely that you're going to have classes inside the margin. And the cost hyperparameter tells the algorithm how bad it is to have cases inside the margin. And the trade-off here is that if you set the cost very, very high, then the algorithm will sort of jump through hoops to absolutely try and find a hyperplane that has as few cases in the margin as possible. And what this often results in is finding a hyperplane that overfits the noise that exists near the class boundaries that you're trying to separate. And what this means is that when you try to use your model to classify future data, your model has overfit to the noise in your training set. The other end of this balance is that if you set your cost too low, then your model doesn't really care that much if there are lots of cases inside the margin, and it becomes insensitive to the real patterns that maybe exist in the data near the boundaries of the two classes. And so there's a trade-off here between overfitting and underfitting. The gamma hyperparameter kind of controls how attention-seeking each individual case is in the data set. So if you increase the value of gamma, then every case in the data set is kind of jumping up and down and shouting, me, classify me correctly. Whereas if you set this low, then each case is much less attention-seeking. And so you get a similar kind of trade-off with gamma as you do for the cost hyperparameter. So if you set gamma too high, then you'll start fitting the noise in your training set rather than finding real patterns that will generalize well to future data sets. Whereas again, if you set your gamma too low, then your model will be insensitive to real patterns that exist in your data. One way to set hyperparameters would be for you to maybe use some existing knowledge of settings that work well and apply those. But that's kind of a naive approach because it's very unlikely that you're going to pick a combination of those hyperparameters that will result in a model that performs optimally. And so a much better thing to do is to perform a process called hyperparameter tuning, where you allow the models to select a set of hyperparameters that perform the best during the model training process. Okay, and to be able to do this in MLR, it's very simple. But the first thing we need to do is define a hyperparameter search space. So define the range of values that we're going to search across to find that hopefully optimally performing combination of hyperparameters. And so first what I'm going to start off by doing is defining an object called kernels. And this is just going to be a vector of the different kernel functions that I want to try during my tuning process. So this is going to be polynomial, radial, and sigmoid. And notice that I've omitted the linear kernel only because if I include the polynomial kernel and I also include the first degree polynomial, then that is equivalent to the linear kernel. And then actually that's something that I forgot to mention. So I mentioned that we have this degree hyperparameter, and that degree hyperparameter corresponds to the degree of the polynomial. Okay, so if that's 1, then we have a linear polynomial. If it's 2, we have a quadratic polynomial, and if it's 3, we have a cubic polynomial. Okay, and that only applies when we're using the polynomial kernel.